And now we're going to talk about the areas of parallelograms and triangles. When we think about parallelograms, I like to think of parallelograms as sheared rectangles. It's just a lot easier to remember the formula this way. And let me show you what I mean. So let's say we had ourselves a parallelogram here that had the following dimensions. So remember, a parallelogram, the opposite sides are parallel. Okay, so this is parallel and those two are parallel to each other. Okay, so there's several dimensions that might come into play. The first is this base down here. Let's imagine we have a base of 10 meters. Now you might know the length of this side right here. Let's say we happen to know that that one had a length of 5 meters. It turns out that's not very interesting in most situations. What we actually need to know is the height here. Sometimes we call this the altitude. So it turns out what we really need to know is the distance, the perpendicular distance that separates the top base and the bottom base. In this case, let's assume that that distance is 4 meters. Okay, so it turns out these are the dimensions we need. This side over here, not particularly helpful in most situations when we're finding the area. So what we say is the area, the formula is going to be area equals base times height. And again, the base is this dimension right here. And then the height is this dimension right here. In other words, what we get is that this area for this particular parallelogram is 10 meters times 4 meters. Okay, when we work it out, that's going to be 40. And the units, remember, meters times meters, so it's meters squared. You can think of this as being what I said before, right? A sheared rectangle. So if I was to take this parallelogram and kind of straighten it out, what I would think about is the dimensions of the base. Well, that's certainly not going to change, right? This is going to be 10 meters. And when I bring them up, what's going to happen is this dimension right here is actually 4 meters. That's 4 meters, not 5. And I'm going to show you in a second why that happens, right? So these two areas of this parallelogram and this rectangle are identical. And here's how we can imagine that. So I've got some 3x5 cards here. And what I've done is I've drawn in a rectangle on this, right? So can you see, we've got a rectangle here. Now, if I was to take that, so again, this is my base, this is my height. Now, let's turn it into a parallelogram. So here I go. Kind of smearing it out. Now, technically what that's called in geometry is a shear. I've sheared this shape. In other words, same area, right? I've got the same number of cards. The area of this edge is the same as before. I've just kind of shifted them all one way or another. And the same thing happens if I go the other way, right? Boom, 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 right? In other words, the area of this is the same. What has changed, this separation between my fingers is the same whether I've sheared it or I just have the same thing where it's a rectangle, right? And it doesn't matter how far I bring it over, right? I could make this thing like super, super flat, right? The distance between the top and the bottom is the same because it's the number of cards, right? Even though this dimension is getting super long, right? But that hasn't changed this area at all, right? I could just be doing this all day. This could be like almost flat. Still, see how this distance has not changed. The area of the side is still the same, right? That's why what we care about is not the distance along here, the side length, but it's the separation from the top and the bottom, right? When I bring it back again, here's my rectangle. I have not changed the area, have not changed the height. That's why with a parallelogram, think of it as, bringing it back to be straight with a rectangle. Okay? All right, so that's how we remember the formula of a parallelogram. In fact, let me do this. I'm just going to remind us that this is a right angle. Okay? All right, let's use this same idea now, but what we're going to do is we're now going to talk about rectangles. So this time, let's think about the fact that a right triangle is half of a rectangle. Okay? Right triangle, half of a rectangle. So let me show you what I mean. Let's draw the following right triangle. Let's have a right triangle here, which has got a height of, let's say, 3 feet. Remember, abbreviation, if it's a apostrophe, that's a shortcut for saying feet. Let's say my base is 4 feet, right? And again, because it's a right triangle, right, this is 90 degrees. And I've kind of made my life a little easier. I picked a nice simple right triangle, right? This is a 3, 4, 5. So 3, 4, 5 would have, right, my hypotenuse was going to be 5. Now notice I did it in pencil lightly because frankly that's not particularly interesting for me. So let's extend the sides a bit. Imagine I had a rectangle, 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 right? So I didn't do a very good job on that. Let's do that better. I don't like that rectangle. Okay, let's try that again. Well, sort of better. Okay, I better stop because I'll be doing this all day. Trying to make it better and better. So anyway, we've got ourselves a rectangle. Now the area of that rectangle would just be 3 feet times 4 feet, right? That's easy. Well, isn't it pretty obvious that that triangle is half of that, right? Okay, right now, I care about the area of this triangle. That's what we're trying to find. This area right here. So that's the dimension that's interesting, the area of that. Well, we don't really have to look up the formula. That's kind of just sort of instinctually, we can just think about that. It's going to be area equals 1/2 of the area of that rectangle. The area of the rectangle would be base times height, right? Well, that's cool. So let's just figure that out. So I've got 1/2, 4 times 3, right? And that's just 1/2 of 12, right? 12 would be the area of the rectangle, 1/2 of that. So hence the area of the triangle is just equal to 6. Now, I really need to talk about units. This is 6 feet squared. Sometimes we call that square feet. And now we've got ourselves an area, 6 feet squared, 6 feet squared. Okay. All right. Right. Don't memorize it. Just realize that, you know, a right triangle is half of a rectangle. Okay. Well, great. But not all triangles are right triangles, are they? Okay. So now let's use the same trick we did with parallelograms and realize that obtuse and acute triangles are sheared right triangles. Okay. So let's draw that picture. Okay, so let's do the same thing we did with parallelograms. So I'm going to put a right triangle here in the middle. Okay, so my right triangle is going to be in the middle. I'm going to use the same one we did up there a second ago. Right, so I've got 3 feet. I've got 4 feet. Okay, and again, I've got a hypotenuse there. That's 5 feet, right? So I've got 3. I've got 4, and I'm not even going to write the 5 because really not very interesting as it turns out. Okay, now let's do the same thing we did a second ago. I've got my 3x5 cards, but now we're going to look at the other side. Okay, so, oh wow, okay, I kind of did backwards, but all right, it's going the other direction than these cards, but just the concept's there. Okay, so here is my right triangle. Okay. Now, if I shear it, okay, let me just make this a little bigger so you can see better, okay? Okay, so we're going to shear this. Here's the dark part. So the dark part's the triangle I care about. Okay, now, right now it's a right triangle. I'm going to make this acute, right? See how I made it acute? This area hasn't changed, right? Again, what I care about is the separation of my fingers here, right? And let's bring it to an extreme. It's super, super flat, right? Again, I don't care how long this edge is, this side. I don't care about this side length, right? What I care about is the separation between my fingers from the vertex here to the base there, okay? Right? I have not changed the area here just because I sheared it, right? If I put it back, right, this dark area is the same. It does the same thing if I make it obtuse, right? Making it obtuse, I'm shearing it in the other direction, aren't I? Again, I don't care about the length of this. Now, you kind of have to imagine that I extended this, right? So here, let's just steal one of the cards from the top. So if I was to extend this across, right? If I was to extend that, what I care about is how far it is between this and this, right? I don't care that this thing is long, right? This has not changed, has it? Just because I sheared it, mushed it to the side, okay? If I bring it back, the black area is still the same. The dark area is the same, okay? All right, so let's go back to our drawings here. Now, again, this drawing, the side's on the other side, but the concept's the same. So let's draw this now where I have brought it off to the left. In other words, I'm shearing it down off to the left to turn it into an obtuse triangle. So again, the base doesn't change, does it? Right? This 4 feet, still 4 feet. The side length though is going to change, right? If I pull this over, and again, I'm going to do this lightly just because really this dimension, as we all know, and here, let me do something real quick. I'm just going to kind of eyeball it so it looks roughly right. Right? We're going to try and keep the height here basically the same. Right? So I'm just going to bring this across so that it all looks the same. Okay, and I'll do the same thing over here. Right? Let's do that. So it looks basically the same. Right? I'm trying to keep the separation between the vertices the same with these. Okay. All right. So again, I'm going to bring it off to the side here. So the vertex would have been here if it was a right triangle. I'm going to bring that over here, and now here's my triangle, right? Coming over here. Again, I'm doing it lightly because, again, that's not the dimension I really care about. And my third side, I can't call it a hypotenuse, can I? Because it's not a right triangle. Notice this is not a right angle anymore. What I do care about, though, is this distance here. Boom, 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 right? That's my right angle. That is 3, right? Let's say, you know, that this was 3.5. I don't really care that that's 3.5. I'm going to write it down just so we know. But really, what I care about is the separation vertically from that vertex down to the same plane, if you like, or, you know, an extension of the line of the base. So these two areas are going to be the same, right? So, right, I sheared it over, right? So this area in here is the same as this area right here, isn't it? Okay, right? I haven't changed the amount of stuff I have. All I've done is just kind of shifted it around. Okay, same thing's going to happen if I go the other way. Okay, so here's my 4 feet. Okay, here's my 4 feet, and again, I'm keeping this separation the same. See how it's got the same reference line up here? So this time, this is going to be an acute, right? And again, when I connect those, right, it's going to look something like that. Again, I made those light, and again, let's just, again, pretend that this side is 3.5. Now it's the other way. But again, that 3.5 is not very interesting to me. What I really care about, right, is this distance, right, which is 3. It has not changed, has it? So the vertex separation from top to bottom is the same. Right? When I do this, notice this yellow area is always the same. All I care about is the height. Now again, sometimes you have to extend off to the side to find that. Sometimes you have to choose the middle, right? If it's obtuse, you're going to the side. If it's acute and you're doing this one, your height is going to be the one inside of it. Okay? All right. So again, just remember this picture. Pretend you've got, you know, 5 cards. Remember this picture. You're going, look, boom, 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 boom. Pull it out, bring it back. Same area. Okay. Finally, it turns out that, you know, triangles have 3 altitudes. right? I mean, I'm showing all the altitudes kind of going up like this, right? Again, if you think about altitude as you're taking your hand at a right angle, right? Okay, but we could have done that 3 different ways, as it turns out. So I'm going to draw this same obtuse triangle 3 different ways. So, right, here's this one, okay? Okay, now what I could have done, right, which is what I did up here, is I extended this line from the base, and then I said, look, here is this height, right? So here's my height, right? So I'm going to call this my height, right? And I always think it's kind of cool because doesn't a height sort of look like an H because it's got that right triangle? Or right triangle. Yeah, it's a right triangle, but it's got the little right angle symbol there. And then this is what we're calling the base. This side length here. So this distance times that distance, and then half of that because it's a triangle. Okay. But it turns out I could have also thought of the same triangle this way, couldn't I? Right, same triangle. Right, same triangle, but it turns out I'm going to use different distances depending on which height, sometimes we call it the altitude we use. Now, if I was to go from this vertex down, right, to here, okay, and use that as my height, this distance right here, well, okay, now I'm calling this distance my height, but to do that, this is no longer my base, is it? I have to call this the base. This is now my base with regard to this height, right? So it depends which one you're calling the height in terms of which one you call the base and vice versa, right? There's even one more way I could have done this, which is, again, same triangle coming off here, okay? This one, I'm going to kind of turn my triangle a little bit so you can see it. Now let's see this, right? Here's this. Now again, I have to extend my base, extending the base so that I can then get a right angle there. Here's my right angle. So here's my right angle. Again, this time I'm calling this my height. So this side is my base, right? You know, there are times that one or the other might be more interesting, or sometimes it's all we know, right? But just remember that every triangle has 3 different ways you can find the area because there are 3 different altitudes. Now, if you want to remember it, sometimes just take your hand and just make a little right angle, right? Here's a right angle, so I know that this guy extends, so that must be it. Or if I'm coming from the other way, well, maybe I have to turn my hand around. I've got this guy is the base, so this guy is the altitude. Or, well, let's see. There we go. Sometimes you have to switch hands so it lines up better, right? Here's my base, so there is my height. Okay? All right, so again, if you're stuck, if you don't remember the formulas, just remember, pretend you have a stack of 3x5 cards and you're kind of shifting it around. Think of a parallelogram as a sheared rectangle. That's why area equals base times height. It's the height, not the side, that matters. Triangles, on the other hand, right triangles, half of a rectangle. Well, that just means it's 1/2 of base times height. Finally, imagine that obtuse and acute are just a sheared right triangle. All right, I sheared it over this way, or I sheared it over this way. And when you need to, there are 3 different ways to find the area. All right, well, guys, that was fun. Thanks for joining us, and we will see you next video.